Okay, hello and welcome. This has been a very interesting 2 days so far. Biggest learning for me so far from yesterday is I had no idea that FDS was only maintained by 1 or 2 people. That was an absolute shock to me. I thought it would be a crowd this big, working full time. But hopefully you'll find my talk a little bit interesting, talk a little bit about the work I've been doing, and it's related to something called smoke dispersion analysis, which I'll call SDA from here on out. And a little bit about me really quick. My name is Brian. I'm from Vancouver, British Columbia. I'm learning that jet lag is a very real thing. And I'm with a company called SNC Lavalin. We're an engineering, procurement, construction management company, 35,000 employees worldwide, and I'm with the Tunnel Ventilation Group, which is about a dozen employees in Vancouver, Canada. So really brief, I'll try to keep it quick. I know that people are trying to get to lunch. I'll talk a little bit about TVS, tunnel ventilation systems, for those that aren't familiar with them. Move on to SDA modeling, our setup, our methodology, a little bit about results, and then hopefully we have some time for some questions later. So for people that may not be familiar with what a TVS or tunnel ventilation system is, essentially it's a network of fans and dampers that we will install in underground transit systems to help in emergency situations to make sure that we can maintain tenability for evacuating passengers. These are big pieces of equipment, and essentially what we'll do is we'll take a holistic approach, kind of a cradle-to-grave design, and apologize if it's hard to see. But most of the stuff I'll be talking about today kind of falls in line with the second column during the design verification phase, where we want to make sure that the proposed TVS system will work, and we'll do CFD analysis and smoke dispersion analysis. After that, we'll carry through to the detailed design, procurement, installation, testing and commissioning, and then finally hand over to the client and customer. For the underground station analysis that we do, the testing and commissioning phase is a great chance for us to validate our model. We'll have the chance to run the systems, measure airflows, look at different scenarios, but we'll talk a little bit more about that later. So here we just have a cross-section of a typical TVS system. On the left-hand side is kind of where you have the trains running, and on the right you have your fans, your fan assemblies. Now, obviously with light rail transit, a lot of the stations run in very dense urban areas, and we'll need to terminate the smoke discharge grates at grade level. We're not in a process facility where we can simply vent it up high. That would solve all our problems. So there's a lot of consideration that needs to be had during these designs. So this is just a few pictures of a typical TVS installation. See the fan lowering down, and then you have 2 silencer assemblies put together. The overall weight of this is about 9,900 pounds, which is about 4,500 kilograms. Fans can be over 200 horsepower with airflows over 100 cubic meters a second or more. And typically for an underground station, we'll have 4 of these fans. We'll have a pair on the left side and a pair on the right side. And why do we need a TVS? These are just 3 examples of previous tunnel disasters that have occurred. One recently in Moscow where there was over 4,500 people evacuated. 2 terrible incidents in Daegu, South Korea, and Azerbaijan. In South Korea, there was an arsonist that brought gasoline onto the train and set it on fire, causing hundreds of deaths. And also similarly, an electrical fault in Baku caused similarly lots of deaths. And I read a quote saying that these 2 incidents in South Korea and Azerbaijan combined, more people have died in these 2 incidents than all of other road tunnel fires combined in history, which I thought was very interesting. So while people may think it's rare, in the off chance that disasters do happen, the consequences are very large. So going on with the TVS design, typically we'll branch off into 2 methods. The first one being on the bottom here, SES, which stands for Subway Environmental Simulation. It's a very well-respected one-dimensional analysis software used to analyze the tunnels for the 99.9% where there is no emergency. So normal modes, different temperature modes, and maintenance modes. And it's very useful because for the station fire analysis, SES can provide us with boundary conditions. And we'll go on with a CFD analysis, and we'll take these boundary conditions and look at station fires, even with trash cans, and also with trains being on fire. The talk today will be more about the smoke dispersion analysis, which I'll get to. So these are just some typical slides for an underground station report that we'll provide for a client. It's very typical. It's a closed system underground, very well understood. We can also go on to validate the design later during the testing and commissioning phase. And previously in the past, clients have been satisfied with this, but we realize these days clients kind of want to know more. What happens to the smoke afterwards? And there can be effects. So after the smoke has discharged to grade, you can see that depending on wind conditions, there can be an adverse effect to that smoke. And it can affect emergency responders, nearby businesses, even the people that are evacuating. And that's our biggest interest because we don't want to have a short circuit of smoke. And it would be a big irony to see the smoke go back into your station entrances when your TVS was designed to protect the people evacuating. So we use the FDS6 for our design validation, and primarily we're mostly interested in re-entrainment. And also as a bonus, we'll look at nearby sensitive buildings, we'll call sensitive receptors. And it's a very useful tool for us. So over on the left-hand side, you can see a station entrance here. It's a big opening, and during an emergency mode, you'd be intaking a large amount of air because that's what the TVS fans will be pulling from. Just another typical TVS station layout. So I picked this slide because we have both the fans in a vertical and a horizontal configuration, and it's missing a fourth fan on the right side, kind of behind. But the point of this slide is to illustrate that oftentimes the architects will be working within very tight constraints, for example, the boundaries and the spaces they're allowed to have. So we have to do a lot of analysis to make sure that we can accommodate the size of the equipment along with how well it functions in emergency conditions. So talking about smoke temperature calculations as one of the parameters for our analysis, we want to kind of always look at the most conservative scenario because there's a lot of uncertainty that can happen in these analyses. So, for example, in a project of, let's say, 12 underground stations, we'll want to pick the station that has the tallest vent shaft where the smoke will experience the most cooling. And then we'll apply the smoke temperature value across all our simulations to be the most conservative. And we want this cold smoke to try and create conditions where the smoke could possibly linger as opposed to, you can imagine if there was no wind, the vents would simply rise up straight and there would be no risks. We want to minimize kind of the thermal effects during an emergency. For the concentration of discharge smoke, again, we also want to go conservative. So what we'll do is we'll assume that one train on fire will be completely, the smoke that it generates will be completely evacuated by only one set of fans on one side. In reality, that would be split amongst the two pairs, but we can take advantage of this by running both vents in tandem. And since simulation time is very precious, this can help save time. So if we can illustrate that on the right-hand side, you can see that the two pair of vents don't interfere with each other. We can run them both at the same time. The one on the left, you can kind of see that may not be a correct analysis because you have the smoke will be overlapping with each other. So typically for the domain sizing, in North America, we'd like to say go big or go home. The reason for this is you want to kind of model the biggest domain that you can afford. And this is so that you can capture the effects of the nearby buildings as accurately as possible. I mean, these types of analysis, there's a lot of uncertainty, but we want to be as realistic as we can. And I'll talk a little bit more about boundary conditions later. And the three buildings in the middle with the purple roofs, those would be, for example, the proposed station entrances. So for guidance on wind speeds and directions, we can look to ASHRAE, which suggests the most onerous case of 1% wind probability. That translates to about 88 hours a year. And we can also look at, there's a lot of wind data being collected all over the world. You can look at a sample, you can look at a wind rose for examples of what the expected airspeeds will be. And we can translate this all into a logarithmic wind profile and apply that to our model in FDS. Now, as for the wind directions to run, obviously there's 360 degrees. There's lots of different cases that we could be running. If you imagine a project with 12 stations, that's a lot of cases to be run. And with these domain sizes being so large, you can be looking at 20 million mesh cells or more, which could take a significant amount of processing time. So to narrow it down, we can take advantage of something called the street canyon effect. And typically stations will run along major streets, and we can simply just look at 4 directions aligned with the major streets. And you have to use a little bit of common sense. So if a particular design could be a risk, let's say on a northeast scenario, then obviously we'll run a special case for that too. The point is we can save a lot of time, not by running 360 degrees of simulations, but you really have to use kind of engineering judgment on selecting the number of scenarios. The wind profile, ASHRAE also has some more guidance on taking airport wind data on major metropolis areas, and you can translate it to urban or different suburban areas with a different alpha law exponent. And so you can look up this data on the internet for every major city in pretty much in the world, and you can apply it to your analysis. So let's talk a little bit about wind boundary conditions. This is a very interesting portion because if you don't get this right, your simulation will be way off, and we don't want that. So luckily, there's been a lot of different academic research in this field that seems to suggest that you want to have at least 5h in front of your domain, where h is the height of your tallest building. And this is to allow for the boundary conditions to basically develop your wind profile appropriately. And then after your model, you want to have a domain of 15h or more, and that allows for the proper turbulent wake regeneration. Height-wise is also a major consideration. So for example, on the simulation on the top right here, with just a 32-meter height, you can see that's totally incorrect. You can see a lot of momentum dissipation off the ceiling, which is incorrect. If you were to cap off that ceiling, you'd have an artificial acceleration of flow over your building, which is also incorrect. So we want to look at least having 5h or more of height space. Typically for the sides of the model that run parallel with the wind, you want to have a mirror condition, so to avoid any kind of momentum losses out the sides. And then for the ceiling, we'll like to use a free slip condition to maintain the wind profile correctly. And as for turbulence models, I mean, I'll touch a little bit about it. I don't want to open that can of worms of which turbulence model is the best. But FDS uses LES, and I believe the turbulence viscosity model is Deerdorf. In the previous versions, it was Smagorinsky. Fortunately for us, it seems to be, in the academic world, there seems to be some research suggesting that LES is good for this type of analysis. If you feel very strongly against that, come find me at lunchtime and we can have further discussion. For run times, typically we'll obviously want to run the entire wind out of the domain for several hundred seconds, just so that we have a stable wind flow. What we did find, though, is you can kind of get a very quick analysis by looking at the wind even before it leaves the domain to get an idea if your design will pass or fail. And the idea for this is, you can get a very quick snapshot of what you think might happen. Then you can communicate to the architect saying, oh, our preliminary analysis might show that this may not work. I'll let you know in a few days what the final result is. And this way we can take advantage of trying to get communication to the architects as quickly as possible. So measurement and visualization, again, we'll use a combination of data that you can find, if you're lucky, for the particular city of interest. Sometimes you have to fill in the blanks, so you'll need to use Google Maps, which is an invaluable resource, Street View, for example, and measuring out distances. Sometimes you have to draw the CAD in manually yourself. And of course, with tools like PyroSim, it's very, very helpful for us because these FDS files can be hundreds of thousands of lines of code. You wouldn't want to be typing that manually. Now, for the results reporting, typically for guidelines like NFPA 130 and Appendix B, they provide very good guidelines on looking at visibility. For example, for this particular run, the architect was proposing that one of the vents is on the side of the building, and from the visibility slice, you can see that it adversely affects a nearby station. So we have a different, we can report whatever we like, but what we do find very useful for clients is appropriate visualization. So we can use isosurfaces to represent our, for example, in this case, it's our carbon monoxide criteria. So you can set your carbon monoxide to the interest that you would like. And for example, in this example here, we have our smoke vents. The proposed design was kind of going on the back of the building, and the architects want to know, would that affect the front station entrances? So this would be our front entrance or louvers, and then also some HVAC intakes. And by running this wind case with the isosurface, and often you have to present this material to maybe non-technical people or people that don't understand FDS. And this creates a very powerful way for us to interact with our clients. So risk mitigation, what do we do with all this data? The most obvious thing that we can do is look at different vent relocations, adjusting the height. In the case that we can't do any changes to the vent locations, and there could be lots of reasons for that, we can look at perhaps different types of louvers or door intakes that could close during emergency situations while they would remain open during normal operating conditions. We can also look at different ejection velocities to see if that will help with the smoke dispersion. And just for example, in this picture here, due to the proximity of the smoke vents, it was decided, why don't we try raising it just to 2 meters, and then we can install a kind of a rest area for pedestrians to sit in, and then try to cover the area with trees. So this example here showed better results than simply just having the grates at the ground level. And then lastly, we need to work with, we'll get everyone involved, the city officials or nearby building owners, to let them know that there could be a risk during a fire emergency. And then they can then look at whether they need to update their procedures, or maybe if their HVAC intake doesn't have a carbon monoxide sensor, that they could install one, things like that. So outlook in the future, this is what do I have to do when I get back to my office, which is just full of computers. Now, like I said earlier, there's a lot of uncertainties with these kinds of analysis. And for example, we're not capturing large foliage like trees or vehicles. Maybe we could look at Lagrangian particles and drag coefficients to address those kinds of things. But major concern for me is kind of looking at mesh resolutions and computing power. For example, if you look at maybe combining these runs with an underground together with the above ground run, you can do everything at once. But then you're looking at models that are in excess of 40 million or 50 million mesh cells, and the computing power is just not there yet. So for sure, I'll definitely try to keep updated on any kind of large-scale wind validations, particularly in applications in FDS. That would be very interesting, and perhaps look at future applications of where this could be applied. It could be maybe pollution modeling, et cetera. So thanks for your time. This is just a picture of underground station fire verification. We'll test our TVS system, and then hopefully one day in the future we can do the same for above ground modeling. Yep, thank you.
Thank you. Do we have questions in the audience? Yes.
Can you please give me an idea what was the maximum cell size used for your model?
Sorry,
the maximum cell size used for your model?
Maximum cell size? Oh yes, I should have touched about that. Typically in the areas of interest, such as around the station entrances and the smoke vent areas, we'll use maybe a 0.2 meter. Mm-hmm. And for example, regions like 50, 80, 100 meters up in the sky, we can use a cell size of maybe like 1.6 meters. Yeah, but during the areas of interest, we'll look at, it'll be about 20 centimeters.
Lovely. So your domain is quite big actually to achieve 1.6 meter maximum cell size. That's require maybe much more than 20 million.
Yeah, so like the image I showed earlier, the domain size is about 20 million or more. So these runs get huge very quick. So that's something I'm always interested in, trying to optimize these runs, find ways to run them faster, and look at more computing resources.
Hello, that was really good. I'm really impressed with you using computational wind engineering. I'm going to have a talk on this tomorrow as well. But what was interesting for me is how do you choose acceptance criteria for the critical buildings? Because obviously the temperature will not be there, there will be some smoke, but what kind of criteria do you choose to say that this is not valid and this is valid?
Yeah, good question. We always like to go with the most strict possible, and this is to cover all our bases. So for example, if you look at ASHRAE 62.1, they reference a criteria of 35 ppm over a 1 hour period as an acceptability criteria. And obviously our simulations are not looking at a 1 hour time period. They could be much less than that for the escaping passenger. But for nearby buildings, that should give plenty of time. So we'll look at, let's say, for example, 35 ppm, and that should be very conservative.
Okay, Kevin?
Yeah, just curious, what boundary condition are you using to specify the wind speed? Are you just doing it with a, like, just pushing it from one side of the domain, or are you using this mean forcing technique?
Yep, the mean forcing technique was something that I did look at. The results seem to be a little bit inconsistent. So what we did was we looked at just, let's see if I can show you. Just like, for example, a big plane will provide wind, just push the whole thing through.
Okay, thanks.
Yep.
Okay, well, thank you very much, Brian.
Thank you.
It was very good.